My name is Doug. I'm a developer advocate with the Firebase team at Google. As a developer advocate, I get to talk to everyone here today. It's a lot of fun traveling and speaking. I actually don't do that much engineering before, but before I was at Google, I was at a startup called Pulse.io, and Pulse.io was a small company, just 5 of us, 4 engineers and a CEO, and the problem we were trying to solve was called application performance monitoring. So the idea is you had an Android or an iOS app, and you wanted to understand how it was performing on your users' devices in production. So it's kind of a hard problem to solve. How do you collect metrics and send them to a server and aggregate? In particular, one of the things we measured was the speed of your HTTP transactions. So we would know, sort of on an aggregate level, how is your app performing in terms of network. And it's kind of a difficult problem to solve. Eventually, this startup was acquired, and it became what is known today as Firebase Performance Monitoring. So I handed off a lot of my work to other engineers who continue today. But a lot of the original engineering still looks like my code. So I'm still happy to be able to talk about what I did. So if you're an Android developer and you're concerned about the performance of your app, you've probably used systrace before. So Android systrace basically hooks right up into your app over an ADB connection. It's going to collect all kinds of information. You can see here there's knowledge about what the CPU is doing, how frames are going through your app, how, just in general, what is your app doing. There's certain problems with systrace, though. If you've ever used it, you know that it slows your app down a lot. You can only run it on a device or an emulator that's running connected to your machine, and it slows the app down. So you can't just generally collect information about it. You have to know what you're looking for, turn it on, let it collect its information, then turn it back off. That kind of doesn't work very well if you want to monitor in production, because your users' devices, you can't use systrace. You don't want to slow down their app. You want to measure everything as transparently as possible. So the way Firebase Performance Monitoring works is that you install it in your app. It's an SDK that you integrate into your app, and while your app runs, it automatically collects information, sends it off to Firebase and Google Cloud, and eventually populates a dashboard. So after your app has been running for a while, you'll collect some information about HTTP events. You can see here they're aggregated by path. A bunch of interesting information here. I won't talk about it too much. It's pretty straightforward. But if you click into one of these, you can see even more information about how long your transaction took, how big it was, how is it succeeding, is it failing, so is it yielding 200 errors or 500 errors. So you can kind of get a sense of what your end user's experience is actually like. So this is a pretty unique way to get this information. But the problem is that the way we designed the SDK is that we didn't want the developer to write any code. We literally wanted it to be a drop it in and it just works. That would be the lowest friction route possible, which is very handy if you can pull it off. But the question is, how do you build a no-code SDK that collects HTTP transaction information? And turns out when I started at Pulse.io, I had no idea. I had no strategy for how to do this. This was a completely new idea to me. They had a strategy for iOS, but they didn't have one for Android, and so that's what they hired me to do. So when I was analyzing the problem, I thought, well, there's lots of different HTTP libraries out there. So OKHTTP, Java URLConnection, Apache HTTP client. And this was back in 2014. So OKHTTP was newer and Apache had been established. Now it's kind of the other way around. People don't use Apache as much, and most people use OKHTTP. But we had to support all of them. Not supporting one of these is not really an option. The other problem we had is for each one of these libraries, there's no generalized hook into being able to get all this information. And that would be kind of a security problem, right? If you had arbitrary code that could know all of your HTTP transactions, that would be kind of bad, right? You should be able to lock that down if you want. So there are some options for solving this. One option is to modify the app source code. So if you could go into the app source code, look for all of the HTTP transactions and instrument them, you could do that. This doesn't really scale, and nobody probably wants their source code modified by some library. Another possibility that we considered was using a JVM agent. So if you've done Java programming on JVMs and not on Android devices, you might know there's this thing called the agent, which lets you register some code at the time you launch a JVM JVM, and it can basically intercept all of the requests to load classes. This is interesting now because what you can do is, at the time a class is being loaded, you can say, well, to give me the bytes, I'll rewrite them. I'll do bytecode manipulation and then hand that off to the system. And you can use that to instrument your app, which is great for JVMs, but Android doesn't really have this. There's no way to register one of these dynamic agents in Dalvik or Art, which is kind of good. You probably don't want users messing with your code like this. The only other option I could think of was to modify the bytecode of the compiled JVM classes before they get deployed. So somehow hook into the build process, get a hold of all the classes, modify the classes, and then build the app with these modified classes. And it turns out this is the only viable solution. So that's the one, that's the route I went down. So like I said, there's 3 different libraries that are supported. I'll just look at one of them today. This is the simplest example. The idea is I'm going to look for code that looks like this. And in particular, I'm interested in OKHTTP because that signals that the app is about to do some HTTP transaction. So the task is look for this, then change it into something where we can monitor how that URL connection is being used. So if you're here today and you're an Android developer, and if you're, consider yourself advanced, you probably know how the Java or the Android build process works. So you have some Java, and this is kind of a high-level view. You have some Java and some Kotlin. That gets compiled, right? You get a series of classes and jars that come out of that. You take those classes and jars, and then you run them through a dexer. So DX or D8 it takes all those classes, and then it generates a series of dex files out of that. So all of your source code and all the libraries and even some stuff that get injected from the build are all part of these classes and dexes. And then finally, the Android system uses AAPT to bundle that up with all your resources and your manifests, and that's how you generate your final APK. So that's how the whole build process works. There's only one place that I'm interested in here, and that's the link between the classes and the jars and DX and D8. So this is where the code has to go. I had to figure out where does my bytecode manipulation go. It turns out at the time I built the solution, there were 2 build systems in play. There was Ant. If you're a longtime Android developer, you probably remember building your app with Ant. Now there's Gradle. Gradle replaces Ant. I had to support both of those, unfortunately, because that's what our customers were using. So I had to figure out, well, where did these classes come from in the build system? You could probably guess by some heuristics or some convention where all these classes are, but it's good not to guess. Also, how do I hook in this bytecode stuff? Where does this go? Like, how do I put this in the build? And it turns out I could figure out how to figure out after compile but before dex. I could put something in there, but figuring out where those classes come from is actually kind of challenging. So it turns out I had to reach into the source code for the dexer, the dex task in the build system, and find the properties in that object that actually tell it where its inputs are coming from. So this is a simplified view, but you can think of it as a list of files that are classes and a list of files that are jars. And that's everything that you need to know. These are the inputs to DX. And so what I had to do, since these are private and I didn't have any other way to do it, is read those values using reflection at runtime. So reach into the object, use reflection, read those values, and write them with my own. So I had to know where the classes are coming from, then tell Dex, no, don't go use those. Use these other ones instead, and those other ones are the ones that I modified. You might think this is either very clever or very bad. It's maybe both. You shouldn't ever reach into private members for any reason, unless you're a scrappy startup trying to get bought by Google, then it's okay. But the good news is you don't have to do this anymore. If you want to do bytecode manipulation, you can do it in Gradle using the Android Transform API. So the Transform API allows you to correctly hook into an Android build so that after classes and jars are fully generated, you can add a transform, a whole sequence of transforms. And in fact, ProGuard is implemented as a transform now if you're not using R8. But if you're using a regular ProGuard build, this is actually how it gets implemented. And so all these transforms can run on the whole series of classes and jars before they go to DX. Now, what I've implemented, and there'll be a source code, a link at the end of this, and that's my trick to get you to stay through the whole talk. The link comes at the end. You have to wait. But what I've built is a Gradle plugin. So if you've ever built Gradle plugins, this is just another Gradle plugin that uses the Android Transform API. There's a runtime support library that I won't say too much about, but it is a software component here. And then there's a sample app that uses it. So the sample app gets instrumented by the Gradle plugin, loads classes from the companion SDK, so you can see how it works. So it's organized a little little bit like this. The transformer libraries are sibling to each other, so the plugin uses the module in a strange way, and I'll tell you how that works later. But the first thing and the most important thing is the Gradle plugin itself. So the thing that uses the transform API is a regular old Gradle plugin. It looks like this. You can see it's a Java library. It uses Kotlin. It publishes to Maven. It's got a bunch of dependencies. The interesting dependency here is the one in yellow. You might recognize that. That is normally goes into Android builds in the build script part, right? That's a build script dependency. But here, it's a compile dependency. So that's kind of odd, isn't it? Well, it's not that odd because that's where the transform API lives. If I want to use the transform API, I need to have a compile dependency on it. I'm going to assume it's loaded into the build system, which is why it's compile only in this case. In order to build the plugin, all you need is an entry point. So the entry point needs to get defined in the meta-inf somewhere, and this is all Gradle build details. But anyway, there's an entry point, the class that it uses when it loads the plugin, or when it loads the jar. It says, here's my plugin, here's where the entry point is. And the entry point looks like this. Pretty standard Gradle plugin. There's a couple interesting things here. One is, I'm going to use the Android plugin. I need to find it. It needs to be loaded ahead of time, so I'm going to go reach into it. I'm going to say, hey, Android build, give me the Android plugin. Then I'm going to check if it's the right type. Then I'm going to register my transform with it. So this is now the transform API saying, hey, who are you? Where do you live? What do you want to do? I'm going to pass an instance of myself in there so I can start intercepting into the Gradle build. The transform object looks like this. So the transform must declare its own name. It has to declare the types that it's interested in. So it also has to subclass transform. So when you subclass transform, now you have all these methods you have to override. So the first method is get input types. You have to declare what you're interested in. In this case, I'm just interested in classes. I believe with transforms you can also intercept resources, but I don't care about those. So I'm just saying all I want is classes. So tell me if there's a class going through the system. The other thing I'm going to have to tell it is the scope of the classes that I want. So the scope is basically everything at the project level, which is the Android app itself, all of the sub-projects, so other modules in there, and all of the third-party classes. So in other words, this is everything. I want to know about all of the classes that are participating in the build. So that's the scope. The other thing I'm saying here is that this is an incremental build. So I'm going to correctly handle situations where Gradle is doing an incremental build and I don't have to instrument everything. This is important. If you don't say that you can do an incremental build, it will not do an incremental build at all. All the builds will be very slow all the time. So you should do this. You should implement this properly. It's a lot of lines of code, but you should do it. And then at the time the transform is desired, there's a transform method, and it receives a transform invocation object. That's kind of important, and I'll show you that in the next slide. But all I'm doing here basically is finding my extension for configuration purposes. So in Gradle, you use an extension to allow the developer to configure you. And then all I'm going to do is kick off the build. Now, the transform invocation object, this is Java now, not Kotlin. I was showing Kotlin before. This is the interface that you're given. It basically defines a way in the build to get all the inputs. So that's what get inputs, get reference inputs, get secondary inputs does. It basically says, what are all the inputs that are going on in this build? I need to know what they are. And there's this thing called an output provider, which says, well, when I change them, I want to write them out somewhere. Where do I write them? The output provider tells me where to write them. So I need to make use of all of these pieces of information in my transform. So to collect all the inputs and deal with the outputs, this is what the code looks like. Take a screenshot, zoom it up if you want. I'm joking, you shouldn't. It's really boring 200 lines of code is what it is. And it's all been open source. So again, at the link at the end, you can see what this is doing. It is really, really boring code. It's just paperwork. In a pseudocode description, it goes like this. Iterate all the inputs. For each input, iterate all the jars, iterate all the directories. If any one of those needs processing, get the output location, then iterate all the classes within that directory or jar. And if it's a class file, read the bytecode, instrument it, and write it back out. Otherwise, just write it back out. That's what the 200 lines of code is basically doing here. And to be honest, the only interesting part of this is using ASM to make bytecode changes. That's what I'm here to talk about. So ASM is the sort of granddaddy of all bytecode manipulation tools. So there's a bunch of different tools out there. I don't want to talk about them. I just want to talk about ASM because this is the thing that everyone uses. I believe the Kotlin compiler uses ASM to help generate class files. So if you're interested in that, go check it out. ASM has a particular way of dealing with class files, and that is using the visitor pattern. So what it's going to do is you feed it a class, it will visit each property, each thing in the class, and your visitor will get invoked. So if you know how XML parsing works, it's a SAX parser, not a DOM parser. So you're going to have to receive these events as they happen. So at the very, very top level, there's a class visitor. And so your class visitor is going to implement a bunch of members saying, what happens when I visit a class, what happens when I know it's outer class, when it's inner class, what are its annotations, what are its fields, what are its methods. You're going to get called for each one of these. Now notice that some of these visitors return other visitors. So it's a visitor that is saying, I have more information, I need another visitor to call back into that. So if you want to know more about any one of these things, you have to return another visitor. In my case, I'm really interested in method visitor, because method visitor is going to be visited whenever a method within a class file is being parsed. That's where all the code is. That's what I want to change. So I have to provide a method visitor. And within a method visitor, there's even more visitor methods that tell it how to find out the parameters, any more annotations, the code itself. In particular, method instructions. So visit method instruction will be a big deal, and I'll talk about that later. But these are the tools. This is the framework you have to work with when you're doing an ASM transform. Okay, so before we go any further, let's talk about bytecode. If you haven't done any sort of bytecode work, some of this is going to be like, drinking through a fire hose. There's a lot to say here, but I'll try to boil it down to the basic stuff. The JVM has different ways of representing its internal state. So every class in the JVM has a constant pool. There is one constant pool per class. It has precompiled known values, so like strings, integers, references to other things, and they're indexed by position. So it looks kind of like this. If you were to dump out a class file using Java P, which is a JDK tool that lets you dig into the internals of a class, it's going to look something like this. So strings and names and numbers and stuff like that. The indexes are the things that identify them. There's local variables. So with local variables, they're similar to registers in a typical CPU. They're indexed by position, with 0 typically meaning this if it's an instance method. They typically map one-to-one with Java and Kotlin locals. So if you declare a local in Kotlin or Java, you're going to probably going to get a local variable in your resulting class file. And they'll look like this. So that bit of code I showed you earlier, there's 4 local variables and this, and they each have a type and they have a name. We reference them by their slot numbers. So the slot number is what you use in bytecode to call them out. In addition to local variables, there's an operand stack. So with the operand stack, the way it works is you push values onto it, so like constants and locals and fields and all the data you're working with, and then you execute operations against those. So you push a bunch of values on the stack, you operate on them, and then they all get popped off, and the result gets pushed on the stack. To me, it's similar to reverse Polish notation. So if you're adding numbers, it's 5, 3, plus. So the operands come first, the operation comes last. So in Kotlin, if you wanted to add 2 integers, the instructions would look like this. Load one value, push it onto the stack. Load another local value, push it onto the stack. Add those 2. They get popped. Then the result gets pushed back on the stack. This is the understanding how this works was key for me to understand how to do bytecode manipulation in the first place. And I use one weird trick to make this happen to my advantage. In the JVM, there are also stack frames. So every time you call a method, the JVM is going to create a new stack frame for each call. That stack frame contains local variables, it contains the operand stack, and the sizes are known ahead of time. So the compiler knows how many locals are in here, how big the stack can be, and that's the frame. And that whole frame is popped off the stack when a method returns. So I'll use these terms a little bit. If this doesn't make total sense right now, that's okay. But I will use these terms talking in the near future. Okay, so in order to kick things off, I have an instrumenter class. So this instrumenter class is the thing that participates in the transform that receives a class file as input. So the instrument method receives bytes and it returns bytes. You can think of it kind of like almost like a pure function. It is just receiving input, making changes to it, and rewriting the changes. The things to point out here is it's using an ASM class reader. So ASM provides a utility that lets you basically parse all of those fields, all of that information out of a class file, and your visitor will get called in response. Then I need to create a class writer, and so this is kind of an inline class. The object colon is saying, I'm creating a new subclass right here inline. It's going to provide a class loader. Now the class loader normally by default is the current JVM's class loader. That's not going to work for an Android build. For Android builds, I need to provide a class loader that describes all the classes that could ever be put into this Android app. And that's because if you need to know the class hierarchy, like what is it subclass? class? What are its internals that are relative to other classes? We just need to be able to understand what they are using this class loader. Then I'm going to tie the two together by providing an instrumentation visitor. This is my class. This is not an ASM class. This is what's going to receive all the visit calls. So this is going to have all the visits for each of the things in the class. And then I'm going to tell the class writer, okay, now go parse and call my instrumentation visitor with the results. Now you notice that actually one thing I didn't mention, the instrumentation visitor is itself decorating the class writer. So that first argument to instrumentation visitor is what it's going to call through to. So its instrumentation visitor itself is a visitor that calls through to another visitor. And the decorator pattern is going to be very important here. But anyway, what we just put together here basically illustrated like this. You have class bytes, the contents of the class file itself. We're going to send it to a class reader. The class reader is going to invoke visitor methods on the instrumentation visitor. Then that instrumentation visitor is going to invoke visitor methods on the class writer in order to generate the final contents, and that becomes the new output. This is very common to do in ASM builds. The documentation I found didn't help me understand this very well, but this is the primary pattern. If you're using ASM to do bytecode manipulation, you will almost certainly go through this path every time. So what does my instrumentation visitor actually look like? Well, it has to subclass class visitor, and it also takes a class visitor as a parameter. It's decorating the class visitor that was passed in. That actually ends up being the class writer in this case. So we subclass class visitor, we decorate another class visitor, and then we have all these overrides. And I'm only showing 2 of them here, but there's going to be a bunch of overrides for each one of the things that we can visit. The one thing that I'm most interested in visiting, like I said before, is the method visitor. So that this override on the bottom, visit method, that returns a method visitor. This is where the good stuff is going. So if I were to implement this method, this visit method, what I'm going to do here is call through to the superclass. So I need, remember that visit method needs to return a method visitor. I can't just create that on my own. I need to actually get that from ASM. So I'm going to call through the superclass, get a method visitor that would get called with all the invocations for what's in the method itself, and then I'm going to decorate it. So I'm going to put my visitor on top of it. So what I'm going to do is intercept all of these visit calls, and then I'll call through to the decorated visitor if I choose to handle them. So what I'll do here is inside my method visitor, notice that this is subclassing a very special kind of method visitor called an advice adapter. So on that 5th or 6th line down, there's an advice adapter. This advice adapter is provided by ASM, and it basically lets me put bytecode in and around other pieces of bytecode. So this is kind of a convenience layer for doing bytecode manipulation. And there's one method visitor in here that I am particularly interested in. It's called visit method instruction. This visitor will get called any time that it sees that there's a method call within the code of that method. So I'm using method in 2 different ways. Inside the body of the method, if it sees a method call, I get to know about it. And I'm told things like, is it in virtual, is it static, who owns the method, the name, and so on. Before I go any further, though, so we're almost in the good code. That method visitor is very, very close to actually seeing bytecode manipulation. But I want to stand back for a moment and say, what are we trying to do here? What's the ultimate goal? The ultimate goal is, as I said before, I want to look for code that looks like this. I'm interested in this URL connection. I want to get a hold of it. I want to understand how it's being used. And I want to change this code into something that lets me monitor the use of this URL connection. Now, if I take this code and I run it through Java P, I'm going to get something that looks like this. So there's going to be a method in there called make request. You can see the operand stack is a maximum size of 3. There's 5 locals. There's 5 local variables. These are the same ones I showed before. So this is part of the dump. And by the way, the equivalent Kotlin is up in the corner. So that the Kotlin, you can compare the Kotlin to the dumped bytecode. So if we go further into this and look at the instructions themselves, you can kind of see how the Kotlin maps into equivalent bytecode. So you can see starting at index 0, it's going to create a new URL class or instance, pass it a string, invoke the constructor on it. Now we have a variable in, we have an object in local variable 1. Then in the next line of code, all we do is create a byte array of size 15. Now here are where things get interesting. So at line 15, what we're doing here is taking that URL class that was stored in local variable 1 and calling the open connection method on it. At this point, on the stack is going to be pushed the URL connection object. Now, starting at line 19, I was kind of surprised to see that Kotlin actually injects its own code there. I didn't write any of that. I didn't do anything in Kotlin to make that happen. Kotlin said, hey, I'm going to check this for null because I need to know if it's going to be null. You're assuming that it's not null. I don't have any guarantees from the JDK, so I have to check it myself. So that's what it's doing here. Then at line 26, at index 26, what we're going to do is load that URL connection onto the stack and then get an input stream from it. And I won't go through the rest of this. In fact, what I'll do is I'll kind of edit out the hidden Kotlin bits because they're not important to the way the method works. They're just checks. So what we can do is erase all this code for now and then compress the interesting bits down into this. So this is what we're doing. This is what it would look like if you were writing it in Java. So again, line 15, we'll load a URL class from local variable 1, call the open connection method on it. It will return a URL connection, and we'll store that in local variable 3. And then we'll go on and call other methods on it. So that invoke virtual is very interesting to me because that, to me, signals when the app is trying to do an HTTP connection. This is interesting, and I need to change that. I need to do something to that. So what I want is, before I see a call to URL connection, my strategy here is to turn this into a static method that does something that I want instead. So I want to transform a call to open connection into a call to a static method on a helper class that I create. So the idea is that I've already provided some class called URLConnection instrumentation. It has a static method on it called open connection. I'm going to call that instead. And you can see what it's doing is it's calling through to URL open connection, but it's decorating it. We're doing more decoration here. So what we're actually returning in this case is a decorated HTTPS URL connection that looks and behaves just like the original, but I get to intercept the methods and do interesting things with them. So there's a more generic pattern here, and I'll just break this down because the generic pattern is actually more interesting than the specific pattern. So if you have code that looks like this, there's an object with a method on it, you pass it parameters, it returns a result. What I want to do instead is call into a utility class, and instead of calling a method on the object, I'm going to pass the object as the first parameter and then pass it the parameters to the original. And then there's a utility class that decorates the result. So to point this out a little bit more clearly, the object that was the target of the method call now becomes a parameter to a static method. The arguments to the function now become further arguments to the static call. The static method calls through to the original, so it's duplicating the work of the original virtual method call, and then the result is decorated. So whatever that R type is, we need to return another R, otherwise the code is going to be terribly confused, right? It's going to call methods on something that doesn't exist. So we're going to decorate it. We'll subclass R and then decorate it. Now, there's one weird trick to make this happen. All we have to do is look and see what that invoke virtual does. So that invoke virtual, and I'm going to use JVM terminology, what it's doing is it's popping 3 items off the stack. So this is before what the operand stack looks like. This is after what the operand stack looks like. So what invoke virtual is doing is it's popping off A, B, and C. Then it's popping off the object. Then it's making a new stack frame with A, B, and C as locals, and it's calling the function on the method. Then when that happens, the result is pushed back on the stack. The way that static methods work is actually very, very similar with one weird difference. The static method will pop all 4 arguments off the operand stack, all of them, all at the same time, make a new stack frame, make all of those arguments local variables, and then push the result. So notice that between invoke virtual and invoke static, the state of the stack is the same. Either way, we've popped 4 things. The net result is 4 things are popped off the stack. 1 thing is pushed on the stack. So if I just change this invoke virtual to an invoke static, that's the weird trick. That's all I have to do. And then all of the further work happens inside my static method. So this is all we have to do in the bytecode manipulation part, is look for invoke virtual on the interesting methods and replace it with an invoke static that's been constructed to decorate the result that came from the invoke virtual. So what does this look like in bytecode? Well, all I have to do is strike out that invoke virtual that calls the original open connection method and instead invoke a static method that I provide at runtime. And that's where the companion library comes into play. The companion library provides the implementation for that. So how do you do that in code? We'll have to go back to that visitor. We're going to jump back into that method visitor and see how to fill it in to do this work. So here's that method visitor, and there's that one method in there that I said I was interested in. Visit method instruction is called whenever it sees an invoke virtual. Now what I can do is, inside that method, I can check to see if that invoke virtual is interesting to me. So is it a method called open connection? Is it on a URL object? Does it take no arguments and return a URL connection? That's what I'm checking here. So if all of these conditions are true, I know I want to change this. This is interesting to me. What I'll do is, instead of calling through, so I should say, if I'm not interested, all I do is call through to the super and say, well, just put that instruction exactly where it was supposed to be. Don't change it. But if I am interested in it, instead, I'm going to change it into a static call. I'm going to give it, I'm going to point it to my class, my method, and my signature. So what I've done is effectively kind of like changed a symlink in Unix. I've said, instead of going over here to this virtual method call, go over here to this static method call. This is the one weird trick. This is all it takes. Now, in practice, it's a little more complicated than this because I'm interested in potentially many different methods. So I have to check all of those patterns to see if it's something I want to change. But this is really what it boils down to. Now, if I were to look inside the static method, inside my helper class, the static method would look like this. So I'm calling that static method open connection. It takes a URL, it returns a URL connection, and then I look at the class and say, is this a URL connection that I'm actually interested in? I'm interested in HTTP. I'm interested in HTTPS. Everything else I am not interested in. So I will not wrap. I will not do anything with, say, file URL connection or any other type of URL connection out there. Only HTTP I'm interested in. So these are now being wrapped. And inside the decorator itself, that's when I have a chance to intercept all the method calls that the developer could be performing on it. So this is just a small selection. I actually have an obligation in this decorator to override all of the public and protected APIs. I can't not do that. And they all have to call through to the superclass. The one thing that I get to do here is now I know when they call connect or when they get an input stream. I can know how this connection is going. And notice that for input streams, instead of returning the same input stream, I'm actually decorating that as well. So I have this sort of nested layer of decorators that are all sort of listening in on how this input stream is being used. So no matter what API how the developer chooses to use this URL connection, I will know about it, and I can time it, I can measure sizes, I can know the URL, and so forth. So that's pretty interesting. The full implementation of these is sitting in the source code. It doesn't actually measure anything. It shows you how you could measure it, though. To wrap all this up, basically, we're using ASM to replace interesting method calls with interesting virtual method calls with static method calls. So all we're doing is changing an invoke virtual to an invoke static. That's all the bytecode manipulation does. The static method itself, though, is going to call through to the original method and decorate the result. And the decorator then can listen in on how it's being used. This runtime support is provided by a library, so it's just another compile dependency that the developer has to add into their app. Of course, if they don't add this, the app will break because it's going to redirect to a static method that's not there. The decorators themselves have to override all the methods. You can't not override all the methods. Otherwise, you'll break the way that the object works. They always call through to the original. So you want it to always behave exactly like the original, but with your additions of measurement. And they internally measure the results. So this is kind of in a sum, everything that's going on. It took me 3 months to figure this out, though. I didn't know anything about bytecode manipulation. I barely knew how the JVM worked. So hopefully, if you know some of these things, you can construct your own solution. Now, if you are writing a transform, I have a few tips for you. Transforms can be slow for large apps. They have to touch every single class file in the system. When you write a transform, you don't have an option of not processing a class file. You have to process it. Minimally, you have to copy it into the destination folder. So be careful. They can be slow. Be sure to implement incremental builds optimally. This is important for transforms. And also allow the developer to disable it if you don't want it on all the time. So for debug builds, you probably don't need to do bytecode manipulation. So in that case, allow the developer to switch it off. And don't process classes unnecessarily. So if you see a class that you know you're not interested in, maybe based on its name or package name, just skip it. The other weird thing that I had to that I found out by a process of trial and error is that you should not transform the companion library classes themselves. And think about this for a moment. If you're looking for an invoke virtual call in the app code and you want to rewrite it, don't rewrite your own application's invoke virtual. So you have to knowingly skip those so you don't double process and end up in a terrible, terrible infinite loop. And you should also write integration tests against your transform classes. I was very paranoid about this. I constructed a giant suite of tests that actually perform bytecode manipulation, load the new class, call its methods, make sure it does everything it still needs to do. The reason being is that if you're going to rewrite someone's entire application, apparently, it should do the right thing. You should not mess that up. That's very bad for your clients to get a non-working application. And as you're testing, if you do work with this, Gradle has a nice little -t build. What this does is it looks for any changes in your source code and immediately tries to build and publish. This command here, I have it running all the time when I'm developing because anytime I make a change to my transform and I want to test it in an app, this will automatically compile it and publish it to Maven Local, so I don't have to do any extra steps. So those are my tips for you. That's all I have to do. That's all I have today. This URL has all the source code, so please go check it out. Send me feedback if you're interested. I obviously can't share with you the full performance monitoring code today. We might open source that later, but everything that's in here is basically what it's doing today. I think that's all my time. Do I have time for questions? Yep.
Hi, thanks for presentation. You said that this transformation API can be very slow. Can we limit it to specific modules? That would be my first question. And second, is it possible that somebody write a malicious plugin that would insert malicious code in our application, and if we don't check source code, that we don't know what our app is doing at all?
Okay, so the first question is, can you limit this to certain modules? Right now, with my knowledge of the Android Transform API, you can't. You are going to be handed all of the modules, but you can't know like its Maven coordinates. So you're obliged to at least copy all the files and jars into another place. But you can look at all the classes and say, does this package name look interesting to me? And you can figure that out by looking at the path of the class file. That's what I'm doing. So in my point where I say skip the classes that are your own like software, it's basically checking the names of the files and saying, this looks like something that's not for me, so I'll skip it. Your second question, can something maliciously add itself? I don't think so. I mean, the way that I'm hooking into the build is with the Gradle plugin, and the developer has to add a line saying apply plugin, the name of my plugin. So they're knowingly inviting my bytecode implementation into their build. I don't think that any arbitrary code can just apply itself, right? I don't know of a way. I mean, I'm sure that something really malicious could mess with someone's build.gradle in a way that they're not anticipating, and it could do things, but I think the chances of that are pretty slow. So I hope that answers your question. Okay. Yes, we have someone down here. Oh, we have a mic over here.
My question is, are there risks of conflicts between ProGuard or other transformers?
So this gets asked a lot. I don't think there are. And the reason is because ProGuard is going to strip out things that it knows are not necessary. And ProGuard always happens at the end. So if you do a transform, you're going to happen before ProGuard. ProGuard is always going to happen last. But even if ProGuard ran first, it's only ever going to strip out things that it knows is never going to get called. So what my transform is doing is it's looking for invoke virtual with certain names of classes that I'm interested in. And since those are public APIs, ProGuard has no business to change them, right? It could never change that signature. Otherwise, it's going to break any sort of code that's going to make assumptions about what the API surface looks like. So I don't believe there are, but I think you could, in theory, make a ProGuard configuration that mangles public names to the point where they can't be recognized by this sort of transform. But that would be a really bad ProGuard configuration to add, in my opinion. So I'm going to say no, there's no conflicts unless you introduce one knowingly. So, my opinion.
Hi, So thank you for the speech. What's your answer about those kind of clients that are afraid about what can do Firebase, in a privacy-based, like those kind of clients, like a bit afraid of what can do Firebase because it's not open source, and actually we don't know what it's like doing in the background. So what's your answer about these kind of things?
Mm-hmm. The privacy concerns that have been expressed to me, are not don't revolve around what it's doing. Like, I think everyone is pretty clear what it does. People are mostly concerned about the contents of the URL, because we're collecting a URL. For some URLs, you could have like PII in there, right? So that's kind of a problem. So what most people need to know is that we chop off the query string. We don't look at the query string at all. So all of those parameters or arguments are completely invisible. The other thing that happens is we collapse. So if you have a REST-like API that has user IDs as part of a URL pattern, we'll detect those patterns and collapse them down to star. So we will aggregate based on the API surface that your different providers expose. So any of the variables, like in a route, are going to be compressed down to star, and they'll be aggregated together. So between chopping off the query string and aggregating based on URL REST parameters, there's no PII left. There's nothing, and we don't associate anything about the user to that request. Now, we do have this idea of sessions and traces that come from one device, from one use case, but we don't know who did that. There's no linkage between the behavior that we've observed in an HTTP transaction and who the end user is. There's like literally no connection between the two. And all Google products have to go through a privacy review also. So if any time during that review something was found, it would have been flagged and fixed. So we're like very, very aggressive about not collecting PII and associating that. So I don't know if that addresses everyone's concerns, but that's the primary concern that we've heard about. Anyone? Yeah.
Is the transform process different with R8 compared to D8?
Yeah, so the transform, so let me go back to the diagram about with the build process. It's on here somewhere. Yeah, so if you remember this diagram, it doesn't matter if you're using DX or D8, because what we're looking at is classes like Java or JVM class files before they get dexed at all. Now, it turns out ASM does provide tools to parse dex files, and I actually investigated that as a potential option, but I like looking at classes better only because it was compatible with, it was easier to hook into the system, and it's also easier to test locally without being on an Android device. But remember, you insert yourself right there, and so you can't generate anything at this point that's incompatible with DEX unless you just mangle every class file, and then Dexter complains, hey, you've got invalid class files. So I don't think there's anything you can do unless you're very bad at doing it. Yeah.
Yeah, thank you for the presentation. What do you think are the main differences with aspect weaving, traditional Java aspect weaving on basic classes and jars?
Mm-hmm. So you're talking about aspect-oriented programming, like with AspectJ. So just as an interesting point, AspectJ uses ASM internally to do its weaving. So with aspect-oriented programming, my understanding was that you write these things called point cuts, and these point cuts describe some sort of change you want. So a common point cut, for those of you who've never done aspect-oriented programming, is logging. So you can say anytime a method that's called that looks like this, log something, which is really interesting and very powerful. But it's also kind of slow to process. And it also, it wasn't as flexible as I wanted. I wanted to be able to target very specific parts of class files and make them do very specific things. And I didn't find that aspect-oriented programming really gave me what I wanted. Now, also to that point, AspectJ tends to want to work on source files. They do expose an API that lets you work against class files. But to be honest, I just understood ASM better. It exposed a very well-documented API, and I just preferred working with it. That's not to say I couldn't have done an AspectJ type thing, but I liked ASM better. So,
Thank you.
Really good questions. Thank you. Anyone else? Okay, awesome. Well, thank you for your time. Please talk to me later.